All right, today we're talking about stoichiometry, mass stoichiometry anyway, and we'll expand on that another time. I want to emphasize two things. Number one, a lot of students find stoichiometry really challenging. Number two, stoichiometry, if we kind of look at the big idea, the big picture of it, stoichiometry should actually be a fairly simple idea, simple concept. And it's some of the details that we bog down, but also those details, again, we're going to try and make it make sense because it comes down to what I work with and what reactions work with. But we're going to start with making a sandwich. Yeah, a sandwich. Now, a sandwich has a fairly simple recipe, and yeah, there's lots of recipes, and yes, it's a lot of tomato, and yes, I need more bacon, but let's just take that as the recipe. If I were to make that sandwich, that recipe, once, I would need those ingredients. But if I were to make it 5 times, I would need exactly the same ingredients, but a scaled up version of it. If I wanted to make 5 sandwiches, I would need 10 slices of bread. And more bacon and more tomato. Math is hard. If I wanted to make 500 sandwiches, I would take exactly the same recipe and I would scale it up. I would need more of that stuff. And the same thing if it kept going, making more and more. Now I also want to say that at some point, measuring tomatoes by counting them out or by measuring the bacon by counting it out no longer makes sense. I would say, ooh, I want to make 500 sandwiches. I need this many pounds, or we're in Canada, this many kilograms of bacon. That's kind of where stoichiometry is at. And I'm going to use the analogy of a recipe all the time. In fact, I'm even going to use that terminology about recipes. So stoichiometry at its rock bottom is mass relationships within a chemical reaction. Now again, I said we'll expand on it a little bit later because not everything we measure in mass. But for now, that. And then really what it comes down to is scaling that reaction to different amounts. Because if I look at a chemical reaction in its simplest form, it's not a very realistic thing to always expect to do it in that way. Okay, so normally we would read the reaction. You don't really need to write this part down. If I took a reaction though, I would probably very comfortably read it as with 1 molecule of nitrogen reacts with 3 molecules of hydrogen to make 2 molecules of NH3, which is ammonia. And we're pretty comfortable with reading a reaction that way. We're going to have to flip that though in a few minutes. But let's just take that for a minute and say that if I had that reaction and I thought of it in that way, let's say instead of making 2 molecules of NH3, I wanted to actually make 73. I wanted to scale up my sandwich operation. Don't eat this one. I wanted to scale up that reaction just to make 72. What would I do? Well, kind of like the sandwich, I would set up a ratio where I'm using, here's how those ingredients are connected. So 3 molecules, I'm ahead of myself, 3 molecules of hydrogen make 2 molecules of ammonia, the numbers that come from the balanced chemical reaction, the numbers that come from the recipe. And then, well, how many would that mean for 72? And I would solve that ratio to get 108. Okay, take exactly the same idea, move it forward. I'm going to take the reaction, same reaction, you're going to find out I like this one a lot. And I'm going to think of this reaction now in terms of moles, which is still a bit unfamiliar to us, but we know that that's the way that we have to think of reactions. 1 mole of nitrogen reacts with 3 moles of hydrogen to make 2 moles of ammonia. Exactly the same numbers, just as different unit. And we know that that's more realistic because I can't work with single molecules and single atoms of things. It's just not practical. Okay, if I took exactly the same idea and now said, well, let's scale up that reaction that I'm now thinking about in terms of moles, what would I do? I would do the same thing. Now, the other thing I want to point out where we get a little bit unfamiliar or a little bit uncomfortable is that I can have fractions now. I can have decimal quantities of moles where I can't really do that when I'm talking about atoms and molecules. But I would do the same thing. I would say 3 molecules, or 3 moles, now I'm going the wrong way. 3 moles of hydrogen make 2 moles of ammonia. That's the recipe. That's from the balanced chemical reaction. Okay, well, how many would I need to make 4.8? And the math would be the same, and the answer, of course, would be different, but it would be the same idea, 7.2 moles of hydrogen. Okay, so here's where stoichiometry, the heart of it, really comes into it, because what we're doing is I'm taking one thing in a reaction or a recipe, how much of the other thing, and that's really what stoichiometry is, with the exception of 2 translation bits. Now, I also want to point out that in this particular example, I ignored the nitrogen, but it has to be there, right? If I said, how many sandwiches can I make from 18 slices of bread? Nobody's going to say, well, do you have enough tomato? Do you have enough bacon? And the answer, of course, is never enough. But do I have enough of those other ingredients? The answer is yes. All I'm asking about is the bread. So the other parts of the reaction will still be there. Okay, we're just going to do one more or maybe two, we'll see. But if I were to do the same thing, now I'm looking at two different things, right? How many moles of nitrogen need to react with 7.58 moles of hydrogen? So now it's two reactants rather than a reactant and a product. But the answer is the same thing, or at least the same idea. I'm going to set up a ratio based on A, this balanced chemical reaction, the recipe, and B, the scaling up version. So again, 1 mole of nitrogen and 3 moles of hydrogen, that goes together, and then X moles of nitrogen over 7.58. Now, normally when we do ratios, or at least when you've done them in the past, you probably haven't had all that labeling on it, the units and the identifying, which one's nitrogen, which one's hydrogen. I'm going to strongly recommend that, because usually with reactions, there's too many things going on that we lose track of what is what. Okay, but anyway, I ended up with 2.53 moles of nitrogen. I'm going to give you one to try on your own. I'll try and give you the final answer. And just to prove that I know more than one reaction, I'm going to give you this one. How many moles of oxygen are used to produce 5.6 moles of water? Okay. Pause it, work it out, and then when you get there, that should be the answer. And if you haven't done that, okay, but you're going to need to do this on your own fairly soon. Okay, you don't need to write this part down, right? This is just kind of giving you a couple of questions that are basically, the idea is, do these look reasonable? And the answer hopefully is yes. How many grams? Oh yeah, grams, I measure grams. Moles are still kind of uncomfortable to us, it's still new to us, but grams, we've been doing that forever, because mass is something that we can measure fairly easily. So we've got two questions here, neither one of them which you're going to answer, so you don't need to write them down, but both of them are reasonable. Okay, well, let's start with one that we are going to solve and work through, okay, which is kind of the same thing, going back to my second favorite reaction. And what mass of hydrogen is required to react with 31.6 grams of nitrogen. I'm doing bad today. Okay, here's the point. The reaction works according to numbers of moles, the stuff we were doing earlier. We work according to masses, so we need to translate from what I can work with into what the reaction works with, and then back. That's all stoichiometry is. Let the reaction do its thing, but then translations on either end for me. Okay, job one, step one, is take that number, that mass that you were given in the question, and turn that into numbers of moles. Okay, well, that is the question now at this point becomes that. How many moles of nitrogen are in 31.6 grams? Ooh, I know how to do that. That's mass divided by molar mass. So the mass of nitrogen as I'm given, the molar mass of nitrogen coming from the periodic table. And I get that many moles of nitrogen. Okay, step two is let the reaction do its thing. How many moles of one and how many moles of the other? So convert moles that I knew from the previous step, turn that into the moles that I'm looking for, the unknown thing. So in other words, the question becomes how many moles of hydrogen would react with 1.129 moles of nitrogen? That's the number I got from before. Well, that's what we were doing a moment ago, where I'm just looking at the balanced chemical reaction for my recipe and then scaling it up or down, I guess, into the ones that I'm actually have. Turn that into, solve the ratio, turn that into the number of moles of hydrogen. Excellent. Now, I want to know how heavy that is, because I need to work with mass. So now I'm going to convert that number of moles of unknown, the thing that I was looking for, into a mass. And I'm not identifying these things as known, given in the question, and unknown, the thing I'm looking for. So in other words, what mass is 3.386 moles of hydrogen? Well, that's an easy question. That's just number of moles times molar mass, where the number of moles I got from the previous step, and the molar mass is the numbers from the periodic table. And that gives me a total mass of 6.77 grams of hydrogen. Okay? That is the number of grams, that is the mass of hydrogen that I could have got from 31.6 grams. Two things. Number one, you cannot do this in a single step. Two, you must do 3 steps every single time. But that's how I'm going to get from the mass of one thing to the mass of the other thing. Okay, recap. These 3 steps have to be done every single time. Okay? And they're going to look like this every single time. For now, keep in mind though, if I'm talking about volume of a solution, I'm actually going to figure out moles a different way. If I'm talking about something else, I'm going to be figuring out moles a different way. But we are still going to do the same basic idea. What can I measure? Turn it into number of moles. turn that number of moles back into something I can measure. And then in the middle, convert from moles of one to moles of the other. It's that easy. Okay, like I said, you have to do all those 3 steps. Okay, we're going to work through this one together. So, hey, another new reaction. Guy's on fire. What mass of carbon dioxide is being produced from 53.6 grams of water? Or sorry, if 53.6 grams of water was produced. Okay, so I have the mass of known to moles of known. In this case, I was given water. So I have the mass of water. I'm going to find the number of moles of water. Then I'm going to convert from number of moles of water into number of moles of carbon dioxide. It's hard to kind of plan that one out, but I'm going to be using the numbers from the balanced chemical reaction. Then I'm going to turn that number of moles of carbon dioxide into a mass, which is going to be number of moles of carbon dioxide times the molar mass of carbon dioxide. Now, I want to pause here just briefly because I know this is getting kind of long. But I've got a couple of places where I'm using a molar mass, a couple of places where I'm using a number of moles. They're not the same. So number 1 is the molar mass of water. Number 3, or step 3 I should say, is the molar mass of carbon dioxide. Now, you don't have to write out the plan before you approach this, but you probably should have a plan in your mind, and it's going to be a similar plan every single time, which is good, but people do start to forget, and we do start to miss things. Okay, so mass of known to moles of known. That is, the question becomes how many moles of hydrogen, of water rather, are in 53.6 grams. That's it. That's all the question is. Right? At this point, all I need to worry about is how many moles of water do I have? Mass divided by molar mass. You will notice that I'm not using the balancing numbers in this step of the question. The balancing numbers do not show up in this step of the question. Okay, but I do calculate the number of moles of water in that. Second step is convert from moles of known to moles of unknown. So moles of known is water, moles of unknown is the carbon dioxide. In other words, if I have that 2.98 moles of water, how many moles of carbon dioxide am I going to get? Okay, balanced chemical equation. This is where I use the balancing numbers. This is the only place where I use the balancing numbers, and there they are. Okay, well, reaction says 3 moles of carbon dioxide work with or come with 4 moles of water. That's where I use the balancing numbers. Okay, well, I don't have 4 moles of water. I've got 2.98. So how many moles of carbon dioxide? Solve the ratio. The last step is to go from that number of moles that I just figured out. So technically, yeah, you're right, it's now known, but it's the thing I'm looking for, so that's the unknown part. Turn that into a mass. Again, the balancing numbers are not part of this. Is how much mass is 2.235. And again, number of moles times molar mass. It doesn't matter what the reaction is or if it's a reaction at all, the balancing numbers are not part of this step, but the molar mass is. And at that point I got 98.3134 grams of carbon dioxide. Okay, so that's it. And it does become a big question. It's a long question. But it's the same kind of thing every single time. All right, I'm going to give you one to try. I would like you to pause it. I'm going to show you like the answers to each one of these steps, but I want you to pause this thing and work this out on your own, following the pattern that we've established. Okay, and as you get there, after the first step, the number of moles of known is 3.54 moles of water. After you do the ratio step, you should have 4.8 moles of oxygen, and your final mass should be 153.7 grams of oxygen. And if you have not gotten those, please do this. It is important. Okay, I'm going to leave you with this one. I'll give you the final answer, but I'm not going to do the individual steps. Again, pause it, work this out so that you can convince yourself that you know how to do this, not just tell yourself that. Okay. Oop, I didn't show you the picture. I thought I was going to, or the final answer. Okay, big picture. Those are the steps. They have to be done every single time. No exceptions. Even if you get like the odd one where, ooh, hey, like the ratio works out so that I could have skipped that step, you're going to do it anyway. Even if it works out that somehow the molar masses on those two things happen to be the same, you're going to do the 3 steps anyway. Always, always, always. Okay, where we're at right now for stoichiometry. Like I said, later on we're going to add to this because we're going to be talking about solutions, or we're going to be talking about gases, and they're going to be different. Until then, though, this is stoichiometry, and we're just going to practice and practice and practice. Talk to you later.